Hey guys, continuing chapter 12, numerically summarizing data. This one's going to be level, or not levels, measures of dispersion. So the measure of central tendency describes the typical value of a variable. So like our averages, on average, what a value would look like. Now dispersion is the degree to which the data are spread out. So how far are they spread out? So here, this is going to measure the difference between lengths of hair versus length of vacation destination. So those are two very different amounts, but what would be normal within those different measurements? That's what this is. So looking at these two data sets, the data in table 7 are represent the IQ scores of a random sample of 100 students from 2 different universities. For each university, compute the mean IQ score and draw the histogram. So we personally don't have to do that because they have it right here for us. So now looking at this data, what we could do is grab all the information. We could take it over to Excel and find the stats on it. But what we could do here is they graphed it for us. Here we have a histogram. Remember histogram, the bars do touch, so that way we could see the spread over time. This is continuous data. So looking at different scores like that. Well, not actually, this is not continuous data. It's discrete data, but it's displayed in a continuous manner. So that way we could see the different scores here. It's not qualitative data. It's not looking at just the quality of a score. The score actually means something. So now looking at these two, notice that over here in University A, the data starts with the lowest score of 60 and goes all the way up to possibly, I think that looks like 160. So looking at 100 different possible scores versus this one, it goes only from 80 up to 120. So looking at 40 possible different scores. So from between 80 and 120. So there's more dispersion on this one over here than there is on this one. It's more spread out over here. Therefore, the dispersion is greater in this one. This has less dispersion because it's not as dispersed as the other one. And another thing I just noticed, they actually kept the same scale. So from 60 to 150, 60 to, they don't have that little tack mark, but, or 160 over here, from 60 to 160 over here, just so we could see the difference in these two. Okay, both universities have the same IQ or roughly the same IQ, but the histogram suggests that the IQs from University A are more spread out than that is more dispersed than in University B. So while an IQ of 100 is typical for both universities, it appears to be a more reliable description of the typical student from University B. That is, a higher proportion of students from University B have IQ scores within, say, 10 points of the mean. University has scores within like 20, 30 points from the mean. So these are a lot more spread out, or actually 40 points from the mean, 40 points on either direction. So not exactly the best justification of scores. One more thing that I wanted to comment on is over here. Normally, if we were to randomly select one of the students or the student and see their IQ scores, the students over here, we could just as likely get someone that's in the 70s as we can get someone that's in the 140s. So not only do we have students that have lower IQ scores here, but we have students that have above average IQ scores over here too. Looking at this one, generally we see that the IQ scores just go from 80 to 120. So even though this is more predictable, this one has a larger range of scores here. All right, so now the range. So I keep saying the R word. So range denoted as R's of a variable is the difference between the largest data value and the smallest data value. How many different possibilities can this data set take on? So here the range would be largest data value minus the smallest data value. So coming over here, we look at the scores from the last video and we see all of these scores. The smallest data value we noted was, I believe, 62, largest data value, 94. So 94 minus 62 is 32. So now what this 32 represents is we have 32 different possible answers to choose from for each of these students. Some answers might be exactly the same. Other answers are not going to be exactly the same. But this data here takes on 32 different values, or a range of 32 different values. So all students in the class score between 62 and 94 on the exam. The difference between the two, or the best score and the worst score, is 32. Now comes like the meat and potatoes of our dispersion, standard deviation of a raw data set. So standard deviation is based on the deviation about the mean. Population standard deviation of a variable is the square root of the sum of square deviations about the population mean divided by the number of observations in the population n. That is, it's the square root of the mean of the square deviations about the population mean. A lot of different words here, but we could sum it up by the actual computation here. So they said the sum of the dispersions or distribution. What was it? Sum of the squared deviations. There we go. So deviations about the mean squared, and we add all of those up for each of the data values and divide it by n. Once we have that number, we take the square root. So throwing the summation in there, we would have the sum of the deviations about the mean squared divided by n. So now looking at that data, formula 1 is sometimes referred to as a conceptual formula because it allows us to see how standard deviation is met or measure spread. The formula that is equivalent to formula 1, called the computational formula for determining the population standard deviation, it's this value right here. This one's a little bit more complicated to actually achieve, so we won't really see this one too much. All right, next, compute the population standard deviation of the test scores in table 8 used previously. So we have these data values. Let's go ahead and grab that data set so we could see how it's done on Excel. So again, command 5, so that way I could take a snapshot of the data set. And once we get that, we could take it over to Excel, insert data from picture, picture from file. And for me, my screenshot right here. Looks about right. So insert the data, even with those two mistakes. And now we have this data set here. So this is the data that we're going to record. And let's get our formula down as a reference. So here, the standard deviation is equal to the square root of the sum of the deviations. So x minus the mean squared divided by n. So now looking at this, we know what x is. X is all of these values right here. We know what n is, and in this case is 10 because there's 10 different numbers here. We know what that squared represents. So the only thing we have to find, the first thing we have to find is this mean here. So let's just come over here and let's do it right here. So the mean of the data set. So the mean of this data set, and let's get a little recap. In order to find mean, we hit equals average. So average of this data set here. highlight the data, and now we have our average. So the mean is 79. So the first thing we have to do is find the deviation from the mean. So here I'll just say x minus the mean. So now x minus the mean is going to be this entire set here. So for each of these, it's going to be equal to x minus the mean. And again, equal to this value minus the mean. But since we are a little bit lazy, what we're going to do is come over here and put dollar signs around the value we don't want changed. For all of these, it's always going to be x, whatever this value is, minus the mean. And we have a value for that mean right there. So we hit enter. And now that we have our mean locked in, because we don't want that to change, we just drag and drop all the way down, and it gives us all of these data values right here. So now with this, we have the standard or the deviation about the mean. So we have this inside part right here. Perfect. Now the next thing we have to do is take the square of each of these values. So square all of these values. And here, because we don't have like, well, we do have a pretty way, but it doesn't really help us out much to show the squared. We're just going to do caret 2, telling us that we're squaring all of these values. Now that we have that, we hit equals this value raised to the power 2. And since we don't want to do that for all 10 of these, we could just grab this corner and bring it down. And let's just make sure that we're looking at the right numbers. So C12, which is the one right next to it squared, we're getting that value squared. Perfect. So now we have this numerator part. The next thing we have to find is the sum of all of those values. So the sum of all those values is going to just be adding all of these values up together. So the sum of x minus the mean squared. And here the sum, we're just going to take the summation of all of these values. So this is going to be equal to sum of these values, adding all those values up together. 964. So now we have this entire numerator. We just have to find this denominator right here. And the denominator is 10 because we have 10 different data sets. So now the next value we're going to find is, well, the inside part. And that actually would be our variation. They didn't give us that score here or that value. No. All right, so they didn't give us that value, but we know that it's the variance. The variance squared, or just very, very close to this part right here. There we go. And us dividing this number by n, it's going to be this divided by n, which is 10. And lastly, we just take the square root of this value, and it's going to give us sigma. It's going to give us our standard deviation. So equal to square root SQRT of this value here. And now we have our standard deviation. So now we could come over here and say the standard deviation of this data set, its sigma is equal to this value here. And there we go. That's it. Of course, with all of this data, there's an easy way that we could find it. And Excel has a pre-recorded or pre-computed way of computing this stuff. So this is going to be equal to standard deviation, STDEV. So standard deviation, remember we have two different data sets. We have standard deviation of a population or standard deviation of a sample. Here in this one, they told us that it was the standard deviation of the population. So compute the population standard deviation. So standard deviation of a population, we could come over here and grab this data set, the original data set. And it's the exact same number because it's computed the exact same way. So there we go. Shortcut, this is the entire process of, or what Excel does whenever we ask it for the standard deviation of the population. It goes through all of this data right here. I'll show you. So it goes through all of this data right here, and then it spits out our standard deviation. And there we go. So instead of doing all of that, we could just type in standard deviation .p, so standard deviation of a population for this data set. And there we go. Let's see if we missed anything. So here they go about the exact same thing. So the mean's exactly the same for all of them because it's the mean of that whole data set. We subtracted the mean from those values, so found the deviation about the mean. So how far away are we from the mean? And once we have those values, we squared all of those values. Next thing we did is we added everything up. So the sum of all of these values ended up being 964. And after that 964, they just divided it by 10, and that gave us our variance, which they didn't talk about here. The next thing we did was take the square root, and it gave us our standard deviation. So we got the standard deviation of that data set. And here they computed it that other way using that other formula. For right now, we don't have to do all that. We could just do the standard deviation of the computational standard deviation instead of the other one. I don't remember what the other one was called. So remember, I told you there's standard deviation for a population. This was going to be standard deviation of a sample. So remember, with a sample, with the population, a population size, we use a capital N. I don't think we've actually talked about it, but with the population size, we use a capital N. With a sample size, we use a little n. And here we could see a good example. So here's sample standard deviation is this value here. Our sample size is n. Population uses sigma. Population uses big N, and population uses mu. So here with our sample mean is X bar, our sample size is N, our sample standard deviation is S. So all of those are going to be the ones that we use for this, well, for all the statistics. But now the sample standard deviation S of a variable is the square root of the sum of square deviations about the sample mean divided, this time by n minus 1, where n is a sample size. And we're x1, x2, x3, all the way up to xn. Those are the observations. So those are the values that we're taking the standard deviation of. Oh, wrong one. Caution, when using formula 3, be sure that X bar with as many use X bar with as many decimal places as possible to avoid round off errors. So we do want to keep everything a lot tighter. We do want everything to be a little bit easier for us instead of just adding everything up for us, instead of like rounding and having a possible error here or there. All right, but this here, again, this is our computational formula, so we're not going to work with the computational formula. Caution when computing So with both of these, we're dividing by n minus 1, not just n. So that's what makes it different between our population standard deviation and our sample standard deviation. We call n minus 1 the degrees of freedom because the first n minus 1 observations have freedom to be whatever value they wish. But the nth value has no freedom. It must be whatever value forces the sum of the deviations about the mean to be equal 0. So again, we're dividing by the degrees of freedom. We're not dividing by the sample size. All right, so looking at this, compute the sample standard deviation of the sample obtained in previous example. So I'm looking back in section 3.1, we see that Jennifer, Juan, Ryan, and Dave are in that sample. So we're going to use that sample again. So remember Jennifer, Juan, Ryan, and Dave. And let's take it over here. So again, we're looking at Jennifer, Juan, Ryan, and Dave. So let's just highlight these values. So Jennifer, Juan, Ryan, and Dave. This here is going to be our sample size. We don't really care much about the rest of these. So now let's clear this out. And let's take a look at just this data set here. So we have Ryan. Well, actually just these two values. So this is going to be our sample. So sample set is going to be Ryan, Jennifer, Dave, and Juan. All right, so now looking at this sample set, remember we're looking for our standard deviation. And let's see if we could get a couple of spaces here. All right, there we go. That way we could keep everything a little bit more organized here. Oh. So what we're looking at here is S, our sample standard deviation, is equal to the square root of the sum of the deviations squared. So x minus x bar squared divided by n minus 1. So that's our sample standard deviation here. And we're going to find all of these values. So just like we did last time, we first have to find the mean because we know what n is. X is all of these values here, but the mean here, and we are not using this mean right here. That's our population mean. There's no reason for us to use a population mean here. But looking at this, let's find our sample mean. So sample mean is going to be equal to average. So average of this data set. Perfect. Now that we have that, we could find this is all our values of x. Here we're going to find x minus the sample mean. So equal to this value here minus the sample mean. And because we're experts at Excel now, we're going to put $ around the cells that we want to keep frozen or keep fixed. And we just drag and drop and we get all of those values right there. So now that we have this here, now that we have the deviations, we're going to square them. So x minus the mean squared. So equals this value raised to the power 2. Perfect. And we're just going to drag that all the way down. Awesome. Now that we have this value here, we have this entire numerator part. Now we have to take the sum of these values. So the sum of x minus the mean squared, and that's just going to equal sum of these values here. And now that we have this value, we have this entire numerator. We got the sum of all of these values. Next, we're going to divide it by n minus 1. So that's going to be s squared. Before we take the square root of these values, it's s squared. And this is going to be equal to this value divided by n minus 1. So n in this case is 4, so 4 minus 1. There we go, 128. Last thing we have to do in order to get s itself is take the square root of the value before it. So equal to square root sqrt of this value here. And there we go. We have our value s equal to, well, s equal to this cell here. And of course, because this is a very common computation, we have a computation already set for standard deviation here. So S, so this is equal to standard deviation ST DEV. So standard deviation of a population or a sample. Remember, this is a sample set because we got a couple of people from the population of the classroom. So sample, standard deviation of a sample. And we go to the original data set that we're getting the standard deviation of. And that's it there. So simple as that. So let's go back really quick and get a little summary of what we've done so far. And let's get rid of all of this data here. Get rid of all of this data here too. And now starting from the beginning, we could say that our population standard deviation population standard deviation, this is equal to standard deviation of the population because we're looking at the entire population. We get the scores of the population. And there we go. That's our population standard deviation. And now for our sample standard deviation, remember this is denoted by simply S. So S is equal to standard deviation, STDEV, this time of a sample. And the sample ends up being this. And there we go. Simple as that. We don't have to do all the crazy computation by hand. We're able to just input it into the system here and it takes the standard deviation for us or calculates the standard deviation for us. And let's see what they got. So here we have 11.3 for this population standard deviation. I feel like I might have done something wrong here. Oh, I see, they messed up. So this should be the sample standard deviation, 11.3. Perfect. So again, this here is a typo. That shouldn't be sigma. That should be S. So let's scratch that out and say S. The sample standard deviation is all this computation here. And again, here they use the computation formula. They didn't use the theoretical formula. I think that's what they're calling it. They're not using the formula, the popular formula, they use the other one. All right, so use statistical software or a calculator to determine the population standard deviation of the data set listed in table 8. We already did, but here they're using the TI-84, it looks like. And here it gives you a couple more stats on the data, but we're using Excel. Now, interpretations of standard deviations. A standard deviation represents the typical deviation from the mean, such as a standard deviation, or I'm sorry, as such, the standard deviation may be used to judge whether a particular observation is quote unquote far away from the data set. So with that comes a couple of good things. So a good rule of thumb is to consider the observation far away if it's more than 2 standard deviations from the other observations, such as the mean. So the mean, remember, is going to be the middle of our data set. It's what a typical value in that data set looks like. Standard deviation, if we look at anything more than 2 standard deviations away from the mean, it's not going to be a common practice there. So when judging the unusualness of an observation, it is vital that you consider the underlying variation in the data as measured by the standard deviation. When comparing 2 populations, the larger standard deviation, the greater the dispersion or spread of the dispersion. So provided that the variable of interest from the 2 populations has the same unit of measurement. So now going back to this right here, we're going to calculate the standard deviation of this data set. Let's see if we could copy it. So for me, Command-Shift-5. And if we can't copy it this way, we might have to break it up into 2 data sets. Open up a new sheet. And cross your fingers, hopefully it does take in that data set. All right, we have University A, University B. It looks like we're going to have to find where the 2 kind of interact here. So what is it, 78 here? All right, so we know to cut it off at 78. So insert with those there. So let's insert, wrong way. So insert behind it. Okay, there we go. So we have these 2 data sets here, just so we could have a little bit more awareness. I'm going to copy this one. So for me, it's Command-C to copy. Come down here and Command-V to paste. And over here, let's delete this data set and see what we could do with it. All right, so now with this, since we're experts, let's find our population mean. So population mean. So equals average. So average of this data set here. Awesome, that was 100. And now we're going to look at the average or the mean of this data set over here. So equal to average of this data set here. Now that we have average, let's find our standard deviation. So since this is a population, or is it a sample? So use standard deviation to determine more dispersion. All right, so this is a sample, obviously, because we have more than just this many students in there. So actually, this would be X bar, not the mean. Same thing down here, because this is a sample of the data. So now our standard deviation is going to be denoted as S, our sample standard deviation. So STD EV of the sample. And now we take the standard deviation of this data set here. So equal to S here. equal to the standard deviation of this sample, this data set here. And there we go. So this one is almost twice as large as this one here. This one has more dispersion than this one here. Even though we look at the mean is exactly the same for these two. We could clearly see that this one it's a completely different data set. We have more of a dispersion. We have more range covered here. We have more variability here. Down here, everything is very, very close together. There really isn't much room for error there. Let's see. And since we just finished our graphing, let's take a look at these. Should we do one of these graphs? So try histogram. All right, well, we could just ignore this right now. It's going to be a little weird trying to get all of that done here. So here, it's very different than it is down here. So standard deviation is smaller, meaning the variability here is less compact. And that's pretty much it there. So that's what a difference in a data set would look like here. And here they use Minitab, I believe, to compute everything. But now looking at this, so determine variance of the variable from raw data. So they do talk about variance. So the variance of a variable is the square of the standard deviation. So the population variance is going to be sigma squared, sigma looking like a little cursive O. So sigma squared, and the sample variance is going to be S squared. So remember, sample standard deviation was S, population standard deviation was sigma. So we're just squaring those two values. Use the results from sigma equaling 9.8 points and S equaling 11.3 points from the previous example, determine the population and sample variance of the test scores. So now looking at those two, let's go back to this sheet over here and look at the difference here. So here we had our population standard deviation. So now there's two ways that we could get this value here. Just copy this. So here with variance, we could square that. So there's two ways that we could get this value here. And the first way that we could get it is equal to this value squared. So all we have to do is square that value and we get right back to our variance. And same thing here. So for our sample variance, we would just square our standard deviation. So we could do that, or what if we don't have the standard deviation? Should we go back and do all of that work for us? No, let's be a little lazy. So variance is another popular computation. So Excel has a command for it. So equal to variance, VAR. And now is this a population, P, or is it a sample, S? So remember, this data was taken from a population, the population of the entire classroom. So it's going to be variance of a population. And we just come over here, grab the data set and do that. So now that we have the population variance, it's the exact same number that we had right over here. And let's take a look what that action would look like over here for the sample. So equal to variance, VAR. This one was the variance of a sample. So VAR.P, I'm sorry, .S for the sample. And we get the data set that we're looking for the variance for. Hit equals, and it ends up being the exact same value there too. So variance, and at the end of this section, I'll kind of summarize everything that we've learned so far, for the computations at least. But that's how you get your population variance, VAR.P, sample variance, VAR.S for sample. And they do that same thing for us, and they just kind of throw those in there. So whenever a statistic consistently underestimates or overestimates a parameter, it is said to be biased. So to obtain an unbiased estimate of the population variance, divide the sum of the square deviations about the mean by n-1. Just food for thought there. All right, next we have our empirical rules. So empirical rule is used to describe the data that are bell-shaped. So bell-shaped means approximately normal. So if a distribution is roughly bell-shaped, then approximately 68% of the data will lie within one standard deviation from the mean or of the mean. So that is approximately 68% of the data will lie between the mean -1 and the mean +1. And once we finish here, you'll see like a cute picture of this. Approximately 95% of the data will lie within 2 standard deviations of the mean. Approximately 99.7% of the data will lie within 3 standard deviations from the mean. So note we can use the empirical rule based on sample data with X bar used instead of mean, S instead of sigma. So we could see that here. So better picture here. We have our approximately bell-shaped distribution here. In the middle is going to be the mean because this is where majority of the data lies. And within 1 standard deviation, so the difference between here and here is 1 standard deviation. And same thing over here. So that's why we say within 1 standard deviation, 68% of the data will lie within 1 standard deviation. Then this value right here, there's 13.5% on either side. So adding all of that up together, we get 95%. So 95% of the data will lie within 2 standard deviations. And coming way up here, 99.7% of the data will lie within 3 standard deviations. So the reason why we say anything greater than 2 standard deviations is unusual, it's because we're looking at 95% of the data. So 95% is going to make up a huge, 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 huge portion of the data. So within 2 standard deviations, anything outside of that 2 standard deviations is going to be unusual. If it's greater than 3 standard deviations, it might as well not even be in the data set. So that's how you can kind of judge things based on how far away they are from the mean. All right, so use the data from University 1 in Table 7. Determine the percentage of students who have IQ scores within 3 standard deviations of the mean according to the empirical rule. So determine the percentage of students who have IQ scores within 3 standard deviations between, okay, part B, determine the percentage of students who have IQ scores between 67.8 and 132.2 according to the empirical rule. Determine the actual percentage of students who have IQ scores between those two according to, all right, so looking at this here, empirical rule using this histogram must be roughly bell-shaped. So this looks roughly bell-shaped, so we could continue on. The histogram is roughly bell-shaped from the previous examples. The mean IQ score of students enrolled in University A is 100. Standard deviation is 16. So remember, we got that data right over here. So University A, standard deviation is 16. The mean is roughly 100. To make the analysis easier, draw a bell-shaped curve like the one shown below. So we have our, let's go ahead and draw our own bell-shaped curve here. So we have our bell-shaped curve here. Remember, majority of the data is going to surround our mean. So here we have 100. And 1 standard deviation below, we're just going to subtract 16. Remember, 16 is our standard deviation. So we're going to subtract 16. 100 minus 16 is 84. 84 minus 16 is 70, 60. I'll just plug it into a calculator. My head doesn't want to do that math right now. So 68. And 1 more standard deviation is going to be 52. And now to go on the opposite side, we'll keep adding 16. So 116 here. 132 here. And the last one, 3 standard deviations, is 148. So that's how we could draw our bell-shaped. And again, from here, we say that 68% of the data will lie between 1 standard deviation (95% will lie within 2 standard deviations. And lastly, we have 99.7% of our data will lie within 3 standard deviations. So what we could say is 68% of these scores will be between 84 and 116. 95% of the scores will be between 68 and 132. 99.7% of the scores will be between 52 and 148. And anything outside of those are going to be extremely unusual, or I believe the book uses very unusual. But that's how we could do that there. And that's what they did right here. So they went out 3 standard deviations to the left, 3 standard deviations to the right. They actually use 16.1 instead of just 16%. So that's why their numbers are just a tiny bit different than mine. But you could do the exact same thing over here with the, all right, so for part B, since 67.8 is exactly 2 standard deviations below the mean, and 132 is exactly 2 standard deviations above the mean, we would just add these different percentages together and come up with 95% of the data. So ours again was a little bit different because we used a different standard deviation. I just rounded up or rounded down to 16. They kept that 16.1 there. Part C, if 100 IQ scores are listed in table 7, 96 or 96% of those are between 67.8 and 132.2. So this is very close to the empirical rule. So they kind of not matched it, but it worked out in that favor. Part D, based on the figure or figure C, approximately 2.35% of the data plus 0.15 is equal to 2.5% of the students at University A will have IQ scores above 132.2. So looking at that, we would have majority of the data, or just 2.5% of the data being above that score using the empirical rule. But now we have Chebyshev's theorem or Chebyshev's inequality to describe any data set. And this happens, or we use Chebyshev's theorem when, or Chebyshev's inequality whenever our data is not normally distributed. So if it's not roughly bell-shaped, we would use this. For any data set or distribution, at least 1 minus 1 over k squared times 100% of the observations lie within k standard deviations of the mean, where k is any number greater than 1. That is at least 1 minus 1 over k squared times 100% of the data will lie between the mean minus k times sigma and the mean plus k times sigma, for k being greater than 1. All right, so note that, we can also use Chebyshev's inequality based on sample data. So this is going to be used for sample data, whether it's roughly normal or not, or we could use it for data that is not roughly symmetric or roughly normal. All right, so here use data from University A in table 7. And we're going to find those couple of things. So using Chebyshev's inequality within with k equaling 3, at least 1 minus 1 over 3 squared equal to 100% or times 100%. This ends up being 88.9. So I'll show you how they got that number. We have 1 minus 1 over 3 squared. And we're multiplying that by 100% and seeing what we get. So here we have 1 minus 1 over 3 squared. We could find that by using a calculator and finding out the square. And let me find it. All right, so calculator, we have 3 squared. So 3 squared gives us 9. So that means that 9 is the denominator here. And times 100%. And now when we have these fractions, we want to rationalize them. When we're subtracting these two numbers here, what we want to do is make sure that the denominators on these two numbers are the same. So we have to find an equivalent number here to get that denominator the same. So what divided by what gives us 1 with a denominator of 9? So we're looking at 9 over 9. 9 divided by 9 still gives us 1. So it works out there. So 9 over 9 minus 1 over 9 times 100%. And now that we have our denominators the same, we could just add or subtract across the top. So we have 9 minus 1, which is 8. So 8 over 9 times 100%. And now we just have to find out what that value of 8 over 9 is. So 8 divided by 9. It gives us 0.88889. And now we're going to multiply that by 100%, so times 100. And that gives us 88.89. So 88.89%. And that's how they were able to get this value. Oh, went a little bit too far. That's how we were able to get this value right here, 88.9%. So 88.9%, or we could say at least 88.9% of all students have IQ scores within 3 standard deviations of the mean. And since the mean of the data set is 100, the standard deviation is 1.16. At least 88.9% of the students have IQ scores between 100 minus 3 times 16.1. And here, let's clear this out so we could read it. So 3 times 16.1, and we're subtracting that from 100. That number ended up being 51. And when we add it, so 3 standard deviations above the mean, this was below the mean. Now we're going to look at above the mean, and that's 148.3. So within our 88% are somewhere, 88% of the students in University A scored between 51.7 and 148.3. And now question B, using that same data. So since 67.8 is exactly 2 standard deviations below the mean, they kind of use the same way that we saw our data over here, that we drew our picture. They use that same sort of thing. Since that's exactly 2 standard deviations below the mean, 132 is exactly 2 standard deviations above the mean. They looked at Chebyshev's inequality, and this time that's 2 standard deviations, so they use this here. And exact same way, so 1 minus 1 over 2 squared times 100%. So this time it's 1 minus 1 over 4 times 100%, 1 minus, well, not 1, because we want to rationalize it. So 4/4 gives us 1, minus 1/4 times 100%. And from there, 4 minus 1 is 3. So we have 3/4 times 100%. And we know that 3/4 is 75. We could type it into our calculator. And 75 or 0.75 times 100 gives us 75. So 75%. So we could say that 75% of the data fall within 2 standard deviations, or 97, at least 97% of the data fall between 67.8 and 132.2. Part C. If 100 IQ scores listed, 96 or 96% are between these two scores. Notice that Chebyshev's theorem provides a conservative result. So this is data that we found from the previous section. Well, not the previous section, but like the previous subsection. We see that what they did here, so of the 100 scores listed, 96, or we could say 96%. So they looked to see how many were actually between these two numbers. And what they're making a note of here is that Chebyshev's, because we look at this problem right here, and it says that only 75% of the data will fall between those two. Chebyshev's theorem is using, or Chebyshev's inequality is using a conservative result. So they're really, really lowballing it. They're not looking at the actual data. They're saying that even if this data set is not approximately normal, we know that, or approximately normal meaning bell-shaped. So we, like, if this data is not bell-shaped, at least 75% of that data will fall within this like 2 standard deviations, or at least 75% of the data, or 88.9% of the data will fall within 3 standard deviations. And that's based on like the actual inequality, or the empirical rule is based on the data being roughly symmetrical. If the data is not roughly symmetrical, it could be doing something like this. And all they're saying is within 2 standard deviations, we're going to have 75% of the data. Within 3 standard deviations, we'll have at least 88.9% of the data. So not exact, these are not exact numbers. This is just a very, very rough estimate. Empirical rule is a little bit tighter. It's a little bit more predictable because it is bell-shaped, but because we have that sort of inequality, or not inequality, we have that pattern in a bell-shaped distribution. When it's not bell-shaped, when it's all over the place, we lose that predictability. So that's all this is saying here. And that's the end of our slideshow. So if you guys have any questions, go ahead and email me, but if not, good luck.